So it turns out that single slit diffraction is not the only diffraction. There's another kind of diffraction that's a little bit more authentic to, if we're actually probing the geometry of, let's say, certain kinds of crystals or molecules, all right? That kind of diffraction is called a diffraction grating. And a grating is just what you think it would be. It has lots and lots of slits, okay? It's not just a single slit, but it's many, 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 many over the course of a whole grating. And these things are really packed tight together. We're talking microscopic distances between slits. And just like with single slit diffraction, you will see this diffraction pattern on the wall with dark and bright fringes. And if you will go to the slide that says finding bright fringes for diffraction, you're going to see another similar relationship. So the relationship is d sine theta equals m lambda again for a diffraction grating, where d is the spacing between the slits. Okay, now notice it's not the width of the slits when we're talking about a diffraction grating. We're talking about the spacing between the slits, okay? And for that reason, this relationship will give you the bright fringes for a diffraction grating, okay? So it might be a good time to break this down a little bit. Take a look at that, write it down, because it's going away. It's going away, ready? Bye. See you later. So here are our three different situations so far. We have Young's double slit, right? That was d sine theta equals m lambda, and that gives us bright fringes, the location of bright fringes. Okay, we had single slit diffraction, and that relationship is the width of the slit times sine theta equals m lambda, and that gives us the location of dark fringes. Okay, and then we have diffraction gratings. And that goes back to d sine theta equals m lambda, where d is the space between the slits, and that again gives us bright fringes. So you see a pattern here that if the relationship is given such that the distance here is the distance between slits, you're looking for bright fringes. If this distance here is the width of a slit, you're talking about dark fringes. Okay? All right, so just wanted to clear that up. Hopefully that separates everything into its nice little neat categories. One interesting difference between single slit and diffraction gratings, right, is that between diffraction gratings and Young's double slit experiment is the light intensity for double slit is consistent, right? For m equals 0, for m equals 1, for m equals 2, there's this consistent intensity, right? And then for diffraction gratings, you get this strong central maximum, and you get these little tiny mini peaks in between for reasons that we're not going to get into. It's too deep, but you have these small secondary fringes, and that's just kind of interesting to note. It might be something that if you do research in a lab on X-ray diffraction at some point, you might, see and notice, and I want you to know that it's there and something that exists. Okay, let's do misconception question number 2. If you hold two fingers very closely together and look at a bright light, you see lines between your fingers. This is actually really cool. I would check it out. Find a bright light, look at it, and you're going to actually see like little dark and bright fringes between your fingers. What is happening here? First of all, I encourage all of you to try this because it's actually kind of neat. And it's a very simple experiment that you can show to anyone in your immediate world. So A, you're holding your fingers too close together to your eye and you're not able to focus right. Okay. B, you're seeing a diffraction pattern. C, this is quantum mechanical tunneling effect. Or D, the brightness of light is overwhelming your eye. No. You are actually recreating single slit diffraction when you are holding your fingers really close together to a bright light and you see those fringes. Sometimes you might have to squeeze it together enough to actually see the fringes, but hopefully you can see it yourself. You're actually getting a diffraction pattern, so you can prove to yourself that this thing called diffraction actually works. Okay. Again, if we go to the slide that says separating colors using diffraction grating, just like with Young's double slit experiment, if you now don't take just a single wavelength, but you take white light, which is all the wavelengths, and you put it through this diffraction grating, you are then going to get the separation of the colors of the rainbow, because for every different wavelength, you're going to get a different angle. And so you can also use diffraction gratings when you have white light to get a beautiful kind of rainbow effect on the wall. If we had this class in person, I could actually show you a diffraction grating and show you how that white light versus red laser light, for example, will separate into either a rainbow or just bright fringes of red light. Okay, that's it for this video. I'll see you in the next one.